Welcome. Well, normally I'm starting talking, so everybody will jump in. Welcome to the Impact of Blockchain in Cybersecurity session. My name is Satoshi Nakamoto. Okay, so was a joke. It's common to see how familiar with you are from blockchain. Well, my real name is Nico Psanidis. I'm from the center. I'm from Greece. I'm almost lieutenant colonel. I'm working like a researcher the last 3 years. I would consider myself like a web expert. You have seen me several. So before we start, I would like to mention the app. I know that not a lot of people are doing that, so I'm mentioning the app. There is also a survey there. You can see the agenda, and you can rate the session and the speakers. This is for if you are bored or you don't have anything else to do. So here we're not going to talk about Bitcoin. We're going to talk about the technology that is behind. I know that blockchain sounds like a buzzword and there is a lot of hype. I would say that there is a lot of excitement. And we'll talk about how blockchain can resolve some of the cybersecurity challenges, like data integrity, like blocking, identity theft. So let me introduce our panel. From left to right, from you, we have Dr. Hassan Karame. He's the manager and chief researcher and security group of NEC Research Laboratory in Germany. He has a master's degree in Gernot Mellon University and a PhD in Federal Institute of Technology in Zurich. This is translated. And of course, he has a book, Bitcoin and Blockchain Security. So, next, we have Professor Maximiliano Sala. He's a full professor of the Department of Mathematics in the University of the lovely Trento. He's leading also a laboratory cryptography, and he's interested in computation algebra, algebraic cryptography, and lately he's an interest on blockchain technology and in-paid security. And last but not least, seldom seen, Mr. Jamie Steiner. He's the general manager of financial service of our Diamond-sponsored Guardtime. His bachelor degree is in aeronautic engineering from the United States of Air Force Academy. And he has a master's degree from New York Stern School of Business. So I think we have a very balanced panel. Welcome everybody here. So there is a kind of a new updated principle on the design of the new internet, let's say, that we think that the trust should be, the full trust will be on the edges, on every trust decision. So we try to take the security from the central to go to the edges. So is this the blockchain example of something like that? Can we have the internet like decentralized and permissionless? Well, now we'll discuss about blocking identity theft. So have you, well, here in Estonia, we have all our health records in the blockchain, as you know. So how about somebody will manipulate and tamper your blood type? That was a question from the previous president. So in this talk, we'll talk also about one previous discussion we had about PKIs. So how about a PKI blockchain-like protocol that can work without certificate authorities? So we had the previous question, so now we have the floor. Professor, the floor is yours.
Thank you. Thank you. Okay, so disclaimer, I'm a mathematician, so I will be maybe technical, but I try to explain what we mean. So first of all, we're talking about a protocol based on blockchain, which is called BIX, B-I-X, and it is not ours, but we've given some security proofs on this protocol. And they work jointly with other 3 colleagues. 2 of them are there. Okay, so digital identities. So in the digital world, real people are identified by digital identities. And usually what we do in internet is we have a PKI, public key infrastructure. And at the end of the day, we have a pair of keys, cryptographic keys. We have a public key which should be known by everyone. There's no harm in that. And a private key you have to keep secret. Okay. So with your private key, you can prove your identity. Now, usually what happens is that your public key together with your data is put together in a file which is called a digital certificate. And the PKI will explain how to deal with this digital certificate, transmit, validate, etc. Okay. So the most widespread standard is probably X509. You have your digital certificate that in particular contains your public key. You need someone to sign it, and who is this? It's certification authority. It's some entity that you trust with your heart. If we trust certification authorities, then we can communicate in a safe, secure way, even if we don't know each other, just by exchanging our certificates and checking the signature or the CA. But we have a problem here. Centralization is cool, is efficient, but if you have some servers which are the main server, they can become primary targets for a full-scale cyber attacks. And the reason why cyber attacks will target certification authorities is because they guarantee authentication security in the web. If they are compromised, it's impossible to distinguish a fake server from a real one. And in particular, certification authorities are behind the HTTPS, which means behind, for example, all e-commerce in the internet. So they're juicy targets for the attackers. There have been many attacks on certification authorities, and as you can see, they never stopped. So what can we do? Well, it's not so easy. Certification authorities and the whole PKI is very complex. We don't have a proposal to replace everything here. We have a seed or an idea, which is not actually ours. It's our colleague Shed Maftic from Sweden. They proposed a blockchain-based protocol to distribute and manage digital certificates without the need of certification authorities. Okay, but this has a seed idea. So just an initial, for example, in the original protocol, there is no proof of work, because we decided we will delay the aspect of which proof of work, proof of stake, whatever. First, we want the main idea to be sound and secure, and then we'll add these features. So how does it work? Okay, you are a new user. You register yourself to a system which could be like an instant messaging that gives you an identifier. You don't need to be recognized as a real-life identity. It doesn't matter. So you get a number, a code, and that code is you, is the big identifier. Once you are registered, then you interact with the system with a software, which is called a BCA agent, that can be on your PC or on your smartphone. Okay. Now, the core of the idea is here. We want to use different blockchains, all of the same kind. And in a blockchain, we have the big certificates, and it's a chain of digital certificates which is cryptographically double linked. So once you are registered, you present yourself to the system, you say, I want a certificate. So you'll get a certificate that will be attached to the chain, to the already existing one. And when there is a new user, it will be attached to your certificate. So the certificates are attached, one after the other. Okay. Here, that's some of the details, so don't worry about all this, because there is something, what you need to understand is not so complex. So we have, I don't know if better here or there. So this is you, the subject is you. This is your signature, digital signature, already introduced. Then the issuer was the person, the user before you. The last one before you, that's his signature, and the next subject is the guy that came after you. Okay? So there are 3 signatures. Now, the interesting part are these 2 signatures. The backward cross signature is a joint signature that you do and the issuer. So you and the old guy together, you make a signature, and we link. And then the forward cross signature, you and the next guy, together you join sign. And so you're linked. You're linked with the past, you're linked with the future. And it's cryptography link, it can be broken. Okay, that was a cool idea. Then there are special cases. Of course, when the blockchain starts, must start from somewhere. So we have a root certificate, it's the first certificate, and there is nobody before that. So that's a special one. And then, more interesting, is the last certificate, your certificate, if you just arrived, is the tail certificate, is a special one because you don't still have someone in the future. Apart from these two special, the root certificate and the tail certificate, all the other certificates have the same structure. So this is the chain of certificates. Okay. So as it's repeated here, the user that owns the tail certificate will become the issuer for the next certificate. Okay, so you arrive at the system, you say, it's me, okay? You get a certificate from the person, from the last one in the queue, and then another one comes and asks you, can I have a certificate? And you issue to him with cross signature. Now, is this system secure? This was a question by Shed when he came to visit us in Bitcoin event that we did in Trento. Is this secure? Can we give some proof of that before starting doing the proof of work, proof of stake, and consensus algorithm, the other parts, which are important, but the main idea must be secure and sound. So we started working on that. So what kind of attack we can do? The first attack we're thinking is there is a valid chain certificate, and the naughty guy tries to attach certificate to the end without interacting with the protocol. This attack we call a chain lengthening attack. We don't like this. The second attack, there is a valid chain, and the naughty guy tries to modify certificate in the middle. So these are the two kinds of attacks that we formally studied. Okay. So as I said, we are mathematicians. We didn't do experiments with computers. So we provide formal proofs. Now, what is security? So this is just a recap for people not familiar with formal proofs. Any cryptographic schemes base security on the supposed computational difficulty of solving a hard mathematical problem. So there is a mathematical problem that everybody thinks it's hard, and you base the robustness of your cryptography upon that difficulty. For example, the RSA, its security is based on the difficulty of factorize large integers. But in our case, we need the security of ECDSA, which is a signing algorithm whose security lies on the discrete logarithm on elliptic curves. Now, if the curve is well chosen, there is no polynomial time algorithm that can solve the discrete logarithm problems on the curve. Okay. Not known algorithm. Okay. So what's a formal security? Well, you want to prove that the cryptographic protocol is secure. You model the possible attacks, and you prove that if the naughty guy can break the protocol, then he can also solve mathematical problem. And since the mathematical problem is supposed to be difficult, this must not happen. Okay. Of course, you have to choose the parameter of the protocol in such a way to make the mathematical problem difficult to solve. Because at the end of the day, it's true that factorizing is difficult, but if you factorize 15, that's not difficult. Okay, the proof, the detail of the proof can be found in our paper. But here, just to tell you, we have an adversary that tries to break the protocol, and a challenger. The challenger is essentially someone running the protocol in an honest way. So the adversary will make queries. So we'll ask for private keys, we'll ask for encryption, it will ask for decryption. And the target could be to recover a private key or to forge a signature, for example. So you have to define the powers the attacker and his goal. We need hash functions. I think you all know what is a hash function, but just to agree on that. For us, the hash function is just a function from an arbitrary string of bits to a fixed length digest. Okay, that's hash function. And we are interested in cryptographic hash function. They have many different properties. Some are equivalent, some are stronger. To make things easier for you, we just focus on collision resistance. So for us, a hash function will be good, collision resistant. If not possible to find computationally, when I say it's not possible, I always mean computationally, in an efficient way. It's not possible to find two files that will be hashed to the same digest. But we restrict the search of our files to the files that come out from the protocol. Okay. Now, elliptic curve digital signature algorithm is more complex to explain. So now, don't worry about what is an elliptic curve. But we worried about this. It's a scheme that allows to sign something and verifying the signatures. And of course, we need also to generate keys. Okay. What's the assumption that we need? Okay, here we have a formal assumption. First, I read the assumptions formally, and then I'll give you an intuition. So the notion security that we need is that an adversary, given a public key, corresponding secret key, and some signatures, is not able to find a message that he doesn't know and to compute a valid signature for that in polynomial time with non-negligible probability. So what we are saying that if the naughty guy knows the public key and some signatures which are valid that he's collecting from the blockchain, then he must be unable to forge a signature for a message that's never seen before. Okay. So, I don't know if I lost you, but here we are at the theorem. So that's a theorem, so it means that's a proof. There's no saying your experiment went bad, you had problem with the computer, we don't know. No, no, this is a mathematical proof. So, we prove the following. First theorem, if the adversary can perform the chain lengthening attack, so the adversary can attach a certificate which is not valid with certain probability epsilon, then if he can do that, then anyone can build a program which is called the simulator in our language, a program that with probability at least epsilon, it will break the mathematics, which means it will either solve the collision problem for the hash function, so we'll find two files that hash to the same digest, or it will break the digital signature scheme. That's the theorem, but we need to reverse the argument to arrive to the corollary, which is what we really need. So just reversing this, we have the following. If the digital signature scheme is secure, in our sense, and the hash function is secure, in our sense, then the BIGS protocol is immune to the attack. That's a proof. Okay, what about the second attack? The second attack is more complicated because it's trying to modify something in the middle, but the formulation is very similar. So if the adversary can perform the static tampering attack with probability epsilon, so it's able to modify a certificate in the middle of the chain, then it will also be able to break the mathematics with probability epsilon over n minus 1. And to break the mathematics means, in this context, it will be able to solve the collision problem of the hash function, or to break the digital signature scheme. What is this n? Well, don't worry about that. It's just the number of blocks that we have in the chain. Okay. Again, we have to reverse the argument here, and we have the corollary. If the digital signature scheme is secure and the hash function is collision resistant, then the BIGS protocol is immune also to this attack. So putting the two theorems together, if you are using secure cryptographic primitive, signature hash, then an adversary cannot break your system, cannot insert certificates, and cannot modify certificates in the middle. But, of course, maybe there are other attacks that it could do. So we have modeled these two attacks. We also found some improvements on the original paper by Maftich, and a lot has to be studied. But for the moment, we believe that these results are important because they build confidence on the system. So when you present a protocol, everybody could invent a protocol and put cross-signature, whatever, but then you have to prove it's resistant. Okay. So a final discussion, just saying that the big certificates now, so we said it's blockchain. So instead of a certification authority, we have many servers and they all have the blockchains. And so the point is that, assuming this protocol is good, okay, the attacker will have to shut down thousands of servers and not one. So that's why this adds security to the system. Okay. So the conclusion, the security proofs in this paper show that the BICS infrastructure is a reliable structure for storing public identities. The certificates, be careful, are issued and distributed in peacetime, because during the attack, the cyber attacker could attack the last, the tail certificate. And if you attack the server with the tail certificate, nobody else is able to construct new certificates. But it doesn't matter. We have at least protected the past, which is a common feature in blockchain. The past is immutable, and the future we see. Okay. Thank you.
You are too fast.
Sorry.
Okay, so I'm really eager to see if there is a question. Oh, come on. Okay, that means that we understand something. Yeah, well, it's in our proceedings also, so if you want more details, you can find it there. Please.
Yeah, I don't know if I totally understand it to a certain degree, but I do understand PKI. And so in the digital certificate process, and my question when you were talking about the hashing and the fact that this particular protocol is, I guess the first question is, when it hands off the certificate to the next user as a continuation,
Yes?
is it rehashing at each point in time? And is the hash staying on that same system, or is this hashing allocated to a separate system?
I don't, there is no, we don't store a hash, we store the signature, which of course contains the hash. So everybody sees the certificates or anybody else. So I don't know if that's your question. So you have a new certificate that will contain the cross signature. Inside the cross signature, there's the hash.
Understood. Okay, that answers my question. Thank you.
Okay.
Somebody else? Okay, second one.
Can you comment on maybe an overhead and the latency of validating trust in this chain? So once we use certificates according to this chain and we send each other encrypted messages, how much would it take me to validate that you are you compared to the current model?
So if I understand what you mean, so we need to communicate securely. So you send me your BICS identifier. I say, okay, show me your certificate. You show me your certificate.
Okay.
I check it's in the blockchain, and if it is, I believe in your public key. So you can start, and you do the same with me, and then once we believe in the public key, we just start encrypting. There's no problem.
Okay, so upon my existence in the blockchain, you trust me, but you have to validate all the intermediary hashes that I've done?
Okay, well, that's more, yeah, computer science question. And of course, you can use checkpoints. So that's, in principle, the main node will have the whole blockchain.
Okay.
But then usually people will have just a checkpoint. And if he needs to go back, then you will talk to one of the main nodes.
So there's a point that I trust, and then,
Yes.
okay, thank you.
Anybody else? No? Well, I have a question.
Okay.
just to also combine what Hassan said before, do you see any of the trade-offs that Hassan talked about blockchain? I mean, also this protocol is it's born, but do you see, let's say, self-mining problems or performance problems?
Okay, the self-mining problem, we'll try to avoid that with a clever proof of work, but we'll see if we can do that. That's one of the problems why we didn't start immediately with proof of work, because we want to think on an algorithm that will prevent the known attacks. But performance, yes, of course, a centralized server will always be more performant than the decentralized system. There's no way about that. There can't be anything more efficient than a huge certification authority that knows everything in the world, except it's not safe. If that goes down, everything is stopped. So the performance is terrible compared to the present system certification authorities, but it will be more robust as a system in case of attacks.
Okay, Professor, thank you. So I have one mathematical problem also to find me how many candies are in this chocolate.
Thank you.
Okay, that's for you. Thank you. Well, I think we are on the same page and we're on nice tempo. Well, DARPA gave 1.8 million to a award contract to GuardTime for verified blockchain-based integrity monitoring system. Did they invest their money correct?
Let's hope so.
Okay, the floor is yours, Jamie.
Thank you. So I am Jamie Steiner. I'm the General Manager for Financial Services at GuardTime. I'm going to talk today a little bit about blockchain and implications for trust and cybersecurity. What we're doing at GuardTime really builds in a more practical manner upon some of the things that have been discussed by some of my colleagues here. But at a high level, what I'd like to highlight today is a little bit about how we do what we have been doing at GuardTime since around 2008, our philosophy for guarding data against cybersecurity attacks, and to show you some of the practical applications of some of the things that we've built and are continuing to build for DARPA and amongst our other partners and customers around the world. So the traditional approach to data security within an enterprise is really to build this fence around the data, right? And the assumption is that if the fence doesn't have any holes in it, that everything inside the fence must be okay. Our approach is a bit different, which is to say, how can I tag and track all of that data inside the fence and to be able to verify it and verify its integrity on a very granular level that's associated with the data. And once you're able to do that, one of the implications is that you can take that data, you can move it outside your fence, you can give it to someone else inside of a different fence or inside of no fence at all, and they'll be able to verify the integrity of that individual piece of data that they care about. So it's really data-centric security, if you will. So I'll start off by just enumerating the number of things that we would like to be able to prove in order to achieve this result, which is when was the data signed, the signing time, the identity of the person who requested the signature, who signed it, and the fact that it has not been changed since that moment. So time is an important part of this, but also the integrity and the identity. And we're using only hash function-based cryptography to make these sort of proofs and assumptions. So at a high level, what can you use it for? And we'll get into a bit more specifics later on. But from a security standpoint, right, if you can prove the identity of the person who signed it, you can prove that it hasn't changed, and you can prove that it existed at a certain point in time, it's then possible to maintain a known good state over all of the data inside your system. And you can then detect unauthorized changes. Now, there's lots of solutions that do change detection, but they all rely on a database of hashes that you compare it to, and it leaves open the attack that could occur when an outsider or even a privileged insider is able to change the database that you're comparing it to. If you don't know, if you don't have a basis of comparison that you can trust, then all of the comparing in the world doesn't do you any good. So that brings us to the second one, which is insider threats. Using PKI-based security, you entrust privileged users with access to keys, and if they abuse those keys or credentials, then the system, the trust in the overall system is undermined. And this is what happens at certificate authorities. You know, in many cases, some of those examples that were put up there where the certificate authorities were undermined, it was users or employees of that certificate authority who abused or were tricked into misusing their credentials by someone from the outside. And so if they change something maliciously, how do you prevent that? How can you prevent an insider who has privileged access from actually changing anything? Well, our answer is that maybe you can't, but at least you can construct the audit trail of events so that they can't tamper with that, and that at least it will be detectable. So they may be able to change some data somewhere in a database, but there will be a log of that that proves that that was what they did, and if they try to delete things from that log, it will become evidence. So we think of it as tamper evidence, right? This becomes incredibly important in the cloud because everyone has to trust the service provider, and as we move more and more things to the cloud or to the Internet of Things, my fourth point there, how do you actually trust the provider? At the moment, we just do because they're big companies and we hope that they won't lie to us. But it's important to be able to actually prove that in a lot of applications. We've seen this being very important to financial customers who have been very hesitant to move their assets into the cloud precisely because they have regulatory requirements that even if they were likely to trust the service provider, Azure or someone else, they're unable to do that because of the regulatory constraints placed on them. So we've had some introductions to hash functions, and I'm assuming that most of the folks in there in the room know what they are. You can think of them as secure one-way operations. Think of it as a fingerprint. If you leave your fingerprint on the murder weapon, I don't need, if I can get a hold of you and I can take your fingerprint, I can prove that you were touching the murder weapon. But it doesn't necessarily mean that I know who you are if I just have the fingerprint. So I can't go backwards. I have to find you and then compare in order to have that evidence, right? So what we do is we construct a lot of hash trees at guard time, and we use them in a very mundane way, actually. We construct a root value from its constituent parts, and I'll put it over here because I'm right-handed. Essentially, all of these lower-level dots represent a fingerprint of some type of data, and actually at guard time we don't care what that data is. It could be a PDF file, it could be a row in a database, it could be a virtual machine image, it could be a log file entry, it doesn't matter. What we care about is the hash of that data. And so that's 32 bytes, 256 bits. And you pass that up to our service, and we take all of those requests in from all over the world. This is done in a distributed architecture, so you have a server at your location, and other customers have servers at their location, and all of those requests get constructed into a Merkle tree, which has a single root. And in a way, this hash value here represents all of the data that was used to construct it. So essentially, if I and all of my 10 million best friends ask for signatures, and I construct one of these things, in the end we get this one hash value. If I have that hash value and I know my path through this tree, and all I need to know to have my path is these other red dots. I don't care what happened down here because it's all sort of summarized in this dot, right? So this is just how a hash tree works, how a binary tree works. If I can have those little summary bits of information, and I start with my data, and I hash it, and I get the blue value, and I have this sort of piece of evidence that I can use to reconstruct this root value. If I trust the root value, and I have the data in my hands, I can prove that my data contributed to that root value. Simple as that. But we can also use one of these things to validate the time that the signature was actually requested. And the way we do that is, if you go back to my previous diagram, this is the tree. You see those here down here. So we make one of these every second. And depending on how many millions of requests we might get, it doesn't really matter. We come up with one value, and we store that in what we call the calendar blockchain. And it has one entry per second based on POSIX time, which started in 1970. This is the only part that we keep up in the calendar blockchain. This thing we create and we destroy. We don't care about it. The users have their chains, they have their paths through that, and if they care about their data, then they keep the signature, but we don't store it for them. We provide services that can be used to store it, but at a very basic level, it's not like our job to keep track of the signatures for the users. We just keep track of the calendar blockchain. And this one down here just kind of illustrates the passage of time. So it's kind of leaning over on the right, displays from left to right the time that has occurred. And so every moment we get a sort of a new summary root hash value that applies to not only the data that was added in this second, which is, and by the way, this yellow dot up here you can think of being this one down here. So I have one of these things under each one of these dots here, right? So every moment I get a new root hash value at this level, which actually protects not only the data from that second, but from all previous seconds back to the beginning of guard time, which was in mid-2008 is when we started it. And then what do we do with those values, those summary root hash values from the calendar blockchain? We publish them in a newspaper. Why? Well, the theory goes that newspapers are made out of paper and that they last a long time. In the libraries of the world, there are microfiche copies. People have them on their doorsteps in the morning. And if you were to try and change a newspaper and prevent some evidence that you were to fake a newspaper, well, it would be very easy, in theory, for the person to go out and buy their own copy or check in their local library, and they could tell that you were lying. So it's a way of doing tamper evidence. I could present you with a fake newspaper, but it would be easy for you to verify that I'm lying to you because you can get your own newspaper. And this is an idea that actually goes back as far as, I think, the 1600s. People were using this type of theory to provide security and prove that they had done something before someone else in sort of patent type scenarios and what have you. So it's not, again, not a new idea. And by the way, this is just the Merkle tree. We call it a blockchain. It makes it very easy for us to explain when we call it a blockchain, because now people are excited about Bitcoin and proof of work and all the rest of it. And so to explain what we've done, some of you who are paying attention may have noticed that actually I said that we were operating this since 2008, which was actually several months before the Satoshi Nakamoto white paper come out. We didn't call it a blockchain then, but that's kind of an interesting fact that isn't necessarily related to the crux of my presentation. But the point here is that if I want to verify that my data existed at a specific second, a specific moment in time, all I have to do is have that chain again. And I can actually work out, based off of the path, what second it was actually included. And I can verify that by looking at the shape of this path, whether it goes left, and it goes right, then it goes left, or it goes right again. I can verify that it came from a moment that was 1, 2, 3, 4 seconds before this publication event. And the publication event publishes the root hash value for midnight on the 15th of the month, and that's what we commit to. It's a public commitment from guard time that says this was the state of our blockchain at this moment in time. We do this once a month. And some of you might have the question, well, what happens if I sign it here, but I want to verify it here? And there's a lot of complicated answers for that, which I won't be able to get to in the 13 minutes and 6 seconds remaining. But it's a little bit more complicated, but there are ways of doing that. Basically, you have to check with us, and we come up with whatever the intermediate sort of moment in time hash value is. So a KSI signature, what does it contain? I told you at the beginning that it needed to be able to prove 3 things: time, identity, and integrity. So the KSI signature contains everything you need to verify those things, right? And how does it do that? So we'll take a look a little bit about what a KSI signature actually is. In the first part, I had kind of described that aggregation tree. We created a big tree of all the different signatures that were requested. That's sort of, this is a sort of a redacted or truncated view of that. It doesn't branch out and out and out because it would take up the whole slide. But you can see just the path that you get. And then it traces to a moment in time, which is then part of a second Merkle tree here. And then that leads up to the publication event. And so what your signature is really this part here on the left, over here for those of you on the left side of the room. And basically that is encapsulated in what amounts to about a 2 kilobyte signature. It contains your hash value, all the other bits and pieces that you need to reproduce the root hash value, and also the publication code, which you can find in your newspaper. The theory being that if you have some data, you want to verify that it came from a certain point in time, that it hasn't changed, and there's an identity piece in here, which I won't go into terribly much, but these aggregators provide a namespace where you can prove where the signature actually originated in that original tree. Then all you need to do is reproduce the root hash value that was then subsequently published in the newspaper, and you can mathematically work out that it must have come from that moment in time, that it hasn't changed, and the identity piece. So the theory being that the history of data as it gets preserved in the KSI is as hard to fake as the content of the world's newspapers. That's the security proof. Well, the security theorem. Great, so how do you use it? So now that we've proven those three things, we have to develop products and services and solutions that use those three guarantees to do useful things for customers who will then subsequently hopefully be willing to pay us a lot of money. So we've actually created a whole sort of block of services, middleware, and end solutions that depend on those guarantees or utilize them in some way, right? So it's kind of, KSI is down here, right? And this is KSI, the software and the cryptographic stuff, which operates over at API, and you can consume that directly from an end user application. It runs on some secure hardware that we've been building called Black Lantern, which offers runtime guarantees and secure execution architecture. And we have a ledger component, which utilizes KSI infrastructure for proof of integrity, but it takes care of other things like keeping track of who owns what. So in the first talk, we discussed the definition of a blockchain that basically involves secure transfer of assets. At Guardtime, we believe that those can actually be disambiguated, that there are sort of separation of concerns. The blockchain can be described slightly differently. And again, it's just a matter of definitions that you subscribe to. But you can actually separate the blockchain infrastructure in terms of providing immutability of data, and you can provide a ledger component that provides for a secure transfer of assets that's actually built on that trust anchor. And you can have several ledgers or multiple ledgers, as many ledgers as you want, that all rest on that same sort of proof of existence of data, which is provided by KSI. We've also got middleware services that make it easier to consume and use and store and verify the signatures for the data that you're concerned with, and then other types of solution packages that then put those different components together in a useful way for customers to solve a problem that they have. So my role at Guardtime at Financial Services is putting together those solution packages, consuming those middleware services, building ledgers that solve specific problems for customers in the financial industry. And I'll talk a little bit at the end about one of the current solutions that we're building. But for one very simple example, we've got an Oracle database integration. So you have a database record, and it turns out that we think about 30 to 40% of the Oracle databases that are deployed aren't actually consuming relational data. They're just being used for warehousing data over time. And so if you want to prove the integrity of one of these sort of data warehouses, it becomes very easy to give that data table within a SQL database append-only properties, simply by chaining up those records or rows as you put them in and signing each one of them with KSI. And because you can do this in a very scalable way, it's possible to have a signature per row. And those will all ultimately be linked back to the KSI blockchain. You can prove the order that they were inserted. You can actually even do this on the event log that the database puts out, so that if you want to have guarantees about who accessed it, who inserted it, you can read that off of the log, and that will also be traceable back to an entry in the KSI blockchain. We have a GDPR compliance as a service model. We call it Volta, and the idea here is that you've got, today in different enterprises, you've got personally identifiable information. And then GDPR came along and said, well, if you're going to hold on to PII, you've got to be able to prove that the person who owns that data gave you permission to use it. Okay, and you've got to prove that if they retracted that permission to use it, that you delete it from your database. Or if you use it only in a certain way, and that your use of that data is compliant with the permission that they actually had from the owner of the data, and that the data hasn't left the company network. So it's a very severe set of requirements to actually comply with. It's all very well to be able to do these things, but then to be able to prove that you've done them becomes a little bit harder. Companies are interested in proving that they're complied because they can have fines and penalties of up to, I think it's 3 or 4% of global turnover, which for many low-margin businesses would be absolutely crushing. So this solution is designed to take that data, put it in a centralized place. You maintain your PII in Volta, and every time you put something in there, you have an event that contains information about the consent that was obtained. That gets stored and cryptographically linked with the actual data itself. When you change it, when you share it, when it's pulled out of that database, every event that modifies it, uses it, or collects it and analyzes it in some way will then be traceable back to the original data that you got from the customer and the consent form that they signed allowing you to access it. The data structure inside here can be constructed in a way that if you delete something, you can actually prove that it doesn't exist in the database, so it's a proof of inclusion, but also a proof of non-inclusion in the case that it has to be deleted. And then it provides a series of reporting functionality externally that allows you to collate those proofs into nice-to-read reports that can be handed to your auditor to prove compliance. So in summary, the idea is to give companies the ability to quickly and easily demonstrate who's been transacting data, what time those things occurred, and to be able to trace the whole history of permission, withdrawal of permission, and deletion to comply with a number of GDPR requirements. And we can provide this as a service. I promised you that I'd talk a little bit about some ledger applications. So one of the things we've been looking at is an insurance ledger, and then we're actually doing a live, well, we finished the proof of concept, and we're actually moving into production deployment of this, production design and build. And the idea is that you can, in the commercial insurance world, build a direct-to-consumer model and in some ways improve the pricing and the data around risk. So today in the insurance industry, in commercial insurance, something like $3 trillion worth of risk is passed around on what amounts to 6 to 12-month-old information that was probably emailed on a spreadsheet. Different insurers all cover the same fleet of ships. You think about a big shipper like Maersk. They have hundreds and hundreds and hundreds of ships that are worth millions, hundreds of millions or billions of dollars. So not one insurer covers a risk for someone like Maersk. They spread it around. But all of those insurers have different information because, of course, it was provided on a spreadsheet. So how do you create a centralized database that everyone can trust and everyone can prove that the data that they're using to price risk is up to date, is the same as everyone else, so that there's no information asymmetry between different people who are bidding on the same insurance contract. So it's not necessarily a case of transferring value in the form of premiums from the shipper to the insurer or backwards if it's a claim. It's more about how do you construct immutability, provable immutability for the data that they're all relying on. How do you update that in real time? And how do you then enable a different business model in the insurance industry that allows you to price risk in real time and receive updates and do real-time analytics, or price insurance by the voyage, depending on the value of the cargo that's actually being transported. All the data is out there, but people can't trust it, and they don't have a way to get it in a timely fashion. And that way you can see blockchain is really as a technology that's enabling digital transformation as opposed to transfer of value or payments or other sort of things that are sort of traditionally seen as blockchain-type use cases. So we found a lot of interest in this, and we're building this for the insurance industry. So that concludes my talk, and I'd like to take any questions that you might have.
Well, Martin Rubel, present or promote our session here. So I don't think Gartam will have a better speaker than you to talk about that. So you're not.
I'll tell
We're
Martin
not
that
talking
you said I
about
was better.
manager things. We really like any technical question if you have. Okay, I know most of you are thinking already the venue, and you're keeping yourself busy. Okay, so do we have a question? Yes, we have, or you just no? Okay, yeah, okay, yes.
So maybe my mic doesn't work. I can't. But okay. So did you think about replacing the paper, the newspaper distribution mechanism with having a Facebook account, a Twitter account,
We have a Twitter account.
Google
We use
Plus
that too.
account?
We do Twitter too.
It looks to me the same trust assumptions. So it's the same if you put it on online world, but several accounts versus several newspapers on papers, right?
Yeah, it's the same sort of trust assumption. It depends on an esoteric discussion on what's more permanent, whether it's Twitter or a newspaper. We have newspapers that are hundreds of years old, so this is like kind of the ultimate, but of course, paper media is going the way of the dinosaur, and so we distribute that. So we also do in Twitter, we've even toyed around with the idea of putting our root hash into the Bitcoin blockchain. This is something that is possible, right? But for different reasons, we haven't done that yet. It's also possible to take the Bitcoin hashes and put them in KSI. So we could do it, we could think, you can decide for yourself which model you trust more.
Yeah, but I didn't mean Twitter alone. I mean, you diversify the social media where you put into, and then you can let go of any printed material. Because it's the same threat model.
No, it's the same model, and actually, I emphasized the newspaper in my talk, but I don't want to imply that you actually need to go out and buy a newspaper in order to verify a KSI signature. All of these trust anchors are available digitally. We maintain an endpoint where you can receive a digital form of that, and it also tells you where you can find the newspapers to go buy them if you should choose to do that. I don't know if anyone is actually using newspapers in any case. I'm not aware of any court cases where we've had to pull out the newspaper to present to the judge and have him work out the SHA-256 himself. But in theory, that trust anchor is always available. And we have use cases that we handle from our customers where there is a retention period that the KSI signature needs to be validatable for, could be the life of a financial transaction plus 10 years. And you might have a swap or a mortgage or something that lasts 30 years. So you're looking at what could be a 40 or even 50-year retention period. So you want to have media that is durable for a period of time, which is quite long in sort of technology terms. What the world will look like in 30 or 40 years and what media will be available, it's kind of hard for any of us to imagine, but at least we think that paper will last so long.
Fair enough.
Yeah, well covered. Oh, we have a question. That's good. And it will be the last one.
Yeah, and I think you may have already answered it in some ways, but the financial industry, this is where I first heard about Blockcoin, that they were very interested in moving into that realm for actually changing from, at some point in the future, from cash to this process of using Bitcoin and Blockcoin as an actual way of us, transitioning over to this whole new technology. Is there any talk of that or any thoughts of that as far as your company goes?
In terms of enabling sort of a cashless society using distributed ledger technology and that sort of thing? Yeah, I think a lot of people are sort of chasing after that, right? I mean, the reality of why that hasn't happened yet, I think there's lots of reasons why, right? It's new technology, it takes some time to adopt. That's a very general answer. Another answer is, there was another comment from the lieutenant colonel there who his mother doesn't know what Bitcoin is. Well, there are many people who would find it hard to adopt a series of transactions, a way of transacting that required you to understand what a hash function is. I mean, this is a barrier to adoption. Scalability, we talked about a number of transactions before. Bitcoin handles 7 to 10 transactions per second, or at least it did. I think maybe they've increased the block size now. But the Visa network handles I think it's sized for something like 10,000 transactions per second. So scalability is a big concern for you to be able to really truly transition to this. Probably the way that it first starts out is within the interbank market, where they can build a private permissioned sort of ledger, hopefully backed by a blockchain, and they can do intrabank transactions. So there's lots of different companies that are trying to build solutions for these types of markets. The reason why we're interested and why I'm interested in the insurance market is in the interbank market and in some of these sort of cash payment type use cases and markets, the margins are already so razor thin. I mean, you're talking about securities settlement. There are pennies on what amounts to millions of dollars worth of transactions. So it's very difficult to sort of improve against that from an economic standpoint. On the other hand, I was in London a few months ago, and I was walking around in sort of the insurance sector, and I see, you know, an insurance adjuster walking between buildings with a huge ream of signed papers under his arm, and I wonder how much money he makes to live in central London in order to carry those papers around for wet signatures. So the margins are actually staggering in comparison. You're not picking up nickels in front of steamrollers. You can really add a lot of value or slice away a lot of cost in the insurance industry. So from a commercial perspective, I think we have found a really good use case to tackle.
Thank you. Thank you. Well, I don't have any cold joke for you, so
I'll just take my
you can
chocolates,
take
thank
the
you.
chocolates.
Okay.
Well, we need to thank our panel one more time.